Stephen Hawking once said, "Intelligence is the ability to adapt to change." This profound insight would have guided his analysis of one of the most terrifying thought experiments in physics. What would happen if a tiny needle, no bigger than a sewing needle, struck Earth while traveling at the speed of light? While most people might dismiss this as pure science fiction, Hawking would have been fascinated by how this seemingly impossible scenario reveals fundamental truths about energy, relativity, and the catastrophic power hidden within Einstein's most famous equation. The legendary physicist would have immediately recognized that this thought experiment isn't just about hypothetical destruction. It's a window into understanding the relationship between mass, energy, and the speed of light that governs everything from nuclear reactions to the birth and death of stars. Hawking's deep understanding of relativity, quantum mechanics, and cosmology would have informed his analysis of how even the tiniest object, when accelerated to light speed, could unleash forces comparable to the most powerful events in the universe. Hawking would have been both fascinated and horrified by the mathematical reality that emerges from Einstein's special relativity. As any object with mass approaches the speed of light, its kinetic energy approaches infinity, meaning that even a needle-sized projectile could carry more energy than the most powerful nuclear weapons ever conceived. This isn't just theoretical speculation. It's a direct consequence of the fundamental structure of space-time itself. Think about this mind-bending reality. A common sewing needle weighs about 1 gram. If somehow accelerated to 99.9999% of light speed, it would carry kinetic energy equivalent to approximately 100 million tons of TNT, more than twice the energy of the most powerful nuclear weapon ever detonated. At true light speed, the energy would be infinite, making the scenario physically impossible but mathematically illuminating about the extreme nature of relativistic physics. What if I told you that Stephen Hawking's analysis reveals that a light-speed needle wouldn't just destroy Earth, it would demonstrate why the speed of light represents an absolute barrier that protects the universe from infinite destruction? That understanding this impossible scenario illuminates the deep connections between relativity, quantum mechanics, and the fundamental forces that prevent the cosmos from tearing itself apart through runaway energy cascades. This is Stephen Hawking's exploration of the light-speed needle paradox, a journey into the extreme physics of relativity, where impossible scenarios reveal profound truths about energy, causality, and the mathematical structures that govern the behavior of matter and energy at the most fundamental levels of reality. Before we explore Stephen Hawking's analysis of what would happen if a tiny needle struck Earth at light speed and why this impossible scenario reveals fundamental truths about the nature of energy, relativity, and the cosmic speed limit that protects the universe from infinite destruction, hit that subscribe button because we're about to journey into the extreme realm of relativistic physics. Rethought experiments reveal the deepest principles governing reality itself. Stephen Hawking's approach to understanding the light-speed needle scenario would have begun with his characteristic focus on the fundamental physics principles that make such a scenario both impossible and illuminating. The physicist would have immediately recognized that while no massive object can actually reach light speed, exploring what would happen if it could reveals profound truths about the nature of energy and the structure of space-time. According to Einstein's special theory of relativity, the kinetic energy of a moving object is given by the equation E = g1 mc2, where g, gamma, is the Lorentz factor that approaches infinity as velocity approaches the speed of light. This means that accelerating any massive object to light speed would require infinite energy, making it physically impossible. However, examining the mathematical consequences reveals the staggering energies involved in high-speed collisions. Hawking would have been fascinated by how this equation demonstrates that mass and energy are fundamentally equivalent, and that the speed of light serves as a cosmic speed limit that prevents infinite energies from being realized in nature. The impossibility of reaching light speed isn't just a technical limitation, it's a fundamental feature of spacetime that protects the universe from catastrophic energy releases. For a 1-gram needle traveling at 99.9999% of light speed, the Lorentz factor would be approximately 224, giving the needle a kinetic energy of about 2 × 10⁻16 joules, equivalent to roughly 5 megatons of TNT. At 99.9999% of light speed, the energy would increase to about 50 megatons. As the speed approaches light speed, the energy approaches infinity, revealing why this scenario is physically impossible. Think about this like trying to push a car up an increasingly steep hill. At first it requires reasonable effort, but as the hill approaches vertical, the force required approaches infinity. The speed of light represents a vertical wall in space-time that no massive object can climb, no matter how much energy is applied. Recent particle accelerator experiments have confirmed these relativistic effects by accelerating subatomic particles to extremely high speeds. The Large Hadron Collider accelerates protons to 99.9999991% of light speed, and the energy requirements increase exponentially as speeds approach the light barrier, confirming Einstein's predictions with extraordinary precision. Let me ask you something that would have fascinated Hawking. If the universe prevents infinite energies through the cosmic speed limit, what does this tell us about the fundamental relationship between energy, information, and the structure of reality itself? Share your thoughts in the comments below, because this question reveals deep connections between relativity, thermodynamics, and the fundamental limits that govern physical processes. Hawking would have been particularly intrigued by what would happen during the hypothetical collision itself. Even at speeds far below light speed, a relativistic needle would interact with Earth's atmosphere and surface in ways that challenge our understanding of matter and energy. The collision would involve physics beyond our current experimental reach, requiring insights from both relativity and quantum mechanics. As the needle enters Earth's atmosphere at relativistic speeds, it would encounter air molecules with such enormous relative velocity that the interactions would involve extreme high-energy physics. The needle would essentially create a particle accelerator beam through the atmosphere, ionizing air molecules and creating a plasma channel in its wake. The energy deposition would be so intense that it would vaporize everything in its path. The physicist would have been amazed by how the collision would demonstrate the equivalence of mass and energy on a macroscopic scale. The needle's kinetic energy would be converted into heat, radiation, and particle creation, with such intensity that it would create conditions similar to those found in the cores of stars or during the first moments after the Big Bang. Recent computer simulations of high-speed asteroid impacts have provided insights into how relativistic collisions might proceed. Even at speeds of only 10% of light speed, projectiles would create explosion craters hundreds of times larger than their own size, with energy releases comparable to nuclear weapons. A truly relativistic needle would create effects far beyond anything in our current experience. Think of the collision like dropping a pebble into a calm pond, but the pebble is moving so fast that it doesn't just create ripples, it vaporizes the entire pond and everything around it. The energy density would be so extreme that normal matter couldn't exist in the collision zone. Hawking would have also been fascinated by the radiation effects that would accompany such a collision. A relativistic needle would emit intense electromagnetic radiation as it interacts with matter, creating gamma rays and other high-energy photons that could be lethal across vast distances. The radiation pulse alone might cause global devastation even before the kinetic impact. The physicist would have been intrigued by how the collision would create exotic forms of matter and energy. The extreme energy densities involved might produce particle-antiparticle pairs, strange quarks, and other exotic particles normally found only in cosmic ray interactions or particle accelerator experiments. The collision site would become a temporary laboratory for extreme physics. Recent research on cosmic ray interactions has revealed that when high-energy particles from space strike Earth's atmosphere, they create cascades of secondary particles that can be detected across large areas. A relativistic needle would create similar but vastly more intense particle cascades that would affect the entire planet. The physicist would have been concerned about how the collision might trigger secondary effects that could threaten global civilization. The electromagnetic pulse from the impact could disable electronic systems worldwide, while the atmospheric heating might trigger climate changes or ozone depletion that could persist for years. Hawking would have been particularly interested in how the light-speed needle scenario illuminates the concept of causality and relativity. Objects traveling at light speed would experience no passage of time from their own perspective, meaning that from the needle's point of view, the collision would be instantaneous regardless of the distance traveled. This reveals deep connections between space, time, and causality. The physicist would have been fascinated by how this scenario demonstrates that the speed of light isn't just about light, it's about the fundamental structure of space-time itself. The cosmic speed limit applies to all forms of matter and energy, revealing that light speed represents the maximum rate at which cause and effect can propagate through the universe. Recent research in theoretical physics has explored how violations of the cosmic speed limit would lead to paradoxes involving causality and the arrow of time. The impossibility of faster-than-light travel protects the universe from logical contradictions that would undermine the consistency of physical law. Think of the speed of light, like the frame rate of reality itself. Just as a movie can't show events happening faster than its frame rate, the universe can't process cause and effect relationships faster than light speed. This limitation isn't a bug, it's a fundamental feature that makes consistent physical law possible. Hawking would have also examined how the needle scenario relates to his own work on black holes and extreme gravitational fields. The energy density of a relativistic collision might be so extreme that it could temporarily create conditions similar to those near black hole event horizons, where space-time itself becomes severely curved. The physicist would have been intrigued by whether such extreme energy densities might create microscopic black holes or other exotic gravitational phenomena. While the energies involved would be enormous by human standards, they would still be far below the Planck scale, where quantum gravitational effects become dominant. Recent research on high-energy collisions has explored whether particle accelerator experiments might create microscopic black holes, though current energies are far below what would be required. A relativistic needle collision would involve much higher energies, but would still be unlikely to create stable black holes. The physicist would have been fascinated by how the scenario demonstrates the connection between energy density and the curvature of spacetime. Extreme energies don't just affect matter. They affect the geometry of space and time itself, revealing the deep unity between matter, energy, and gravity described by Einstein's general relativity. Hawking would have been particularly interested in the quantum mechanical aspects of the collision. At the extreme energy scales involved, quantum effects would become important, potentially leading to particle creation, vacuum fluctuations, and other phenomena that bridge the gap between relativity and quantum mechanics. The physicist would have been excited by how such extreme conditions might provide insights into quantum gravity, the long-sought theory that unifies general relativity with quantum mechanics. The collision would create energy densities approaching those where quantum gravitational effects might become observable. Recent research in theoretical physics has explored how extreme energy collisions might reveal new physics beyond the standard model of particle physics. The energies involved in a relativistic needle collision would far exceed anything achievable in current particle accelerators, potentially revealing new fundamental particles or forces. The physicist would have been amazed by how the scenario demonstrates that even impossible thought experiments can reveal profound truths about the nature of reality. By exploring what would happen if the laws of physics could be violated, we gain deeper understanding of why those laws exist and what they protect us from. Hawking would have also considered the cosmic implications of the light-speed needle scenario. If such projectiles could exist naturally, they would pose existential threats to any civilization in the universe. The fact that the laws of physics prevent such objects reveals how the universe is structured to allow the existence of stable matter and complex systems like life. The physicist would have been fascinated by how cosmic ray observations provide real-world examples of particles approaching the theoretical limits of the needle scenario. The most energetic cosmic rays carry energies comparable to macroscopic objects, demonstrating that nature does create extremely high-energy particles, though not at the scales required for planetary destruction. Recent observations of ultra-high-energy cosmic rays have revealed particles with energies exceeding 10 to 120 electron volts, equivalent to a baseball traveling at 100 kilometers per hour, compressed into a single proton. These observations show that the universe can create particles with enormous energies, though still far below what would be required for a relativistic needle. The physicist would have been intrigued by how the study of cosmic rays reveals the natural limits of particle acceleration in the universe. Even the most powerful astrophysical phenomena, supernovae, black hole jets, and gamma-ray bursts, cannot accelerate macroscopic objects to relativistic speeds, suggesting fundamental limits on how much energy can be concentrated in massive objects. Hawking would have been particularly interested in how the needle scenario relates to the concept of vacuum stability. The extreme energy densities involved might be sufficient to trigger phase transitions in the quantum vacuum itself, potentially creating regions where the fundamental constants of physics are different. The physicist would have been concerned about whether such extreme energy densities might trigger a vacuum metastability event, a theoretical scenario where the quantum vacuum transitions to a lower energy state, potentially destroying all matter in the universe. While highly speculative, this possibility demonstrates how extreme physics scenarios can have cosmic implications. Recent research in theoretical physics has explored the stability of the quantum vacuum under extreme conditions. While current understanding suggests that the vacuum is stable under most circumstances, the energy densities involved in impossible scenarios, like the light-speed needle push into unexplored theoretical territory. The physicist would have been fascinated by how the scenario demonstrates the interconnectedness of all physical phenomena. What starts as a simple question about kinetic energy reveals connections to relativity, quantum mechanics, cosmology, and the fundamental structure of reality itself. Hawking's analysis would ultimately reveal that the light-speed needle scenario, while physically impossible, serves as a powerful tool for understanding the fundamental principles that govern the universe. The impossibility of the scenario isn't a limitation. It's a protection mechanism built into the structure of space-time itself. The physicist would have understood that the cosmic speed limit doesn't just prevent faster-than-light travel. It prevents the universe from destroying itself through runaway energy cascades. The speed of light represents a fundamental constant that maintains the stability and consistency of physical law across all scales. Recent developments in theoretical physics continue to explore the implications of relativistic scenarios for our understanding of energy, matter, and spacetime. While we may never encounter truly relativistic macroscopic objects, studying their theoretical properties reveals deep truths about the nature of reality. The physicist would have seen the light-speed needle scenario as a perfect example of how impossible thought experiments can illuminate possible truths. By exploring the boundaries of what physics allows, we gain deeper appreciation for the elegant mathematical structures that govern the cosmos. Hawking's investigation would show that even the most destructive scenarios reveal the underlying harmony and protection built into the laws of physics. The universe is structured not just to allow complexity and life to exist, but to prevent them from being destroyed by the very forces that created them. The next time you consider the relationship between energy and mass, or wonder about the cosmic speed limit, remember Stephen Hawking's analysis of the impossible needle. The laws of physics that prevent such catastrophic scenarios are the same laws that allow stars to shine, planets to form, and life to evolve in a universe balanced between creation and destruction. If this exploration of the light-speed needle paradox has deepened your understanding of relativity, energy, and the fundamental protections built into the structure of spacetime, make sure to smash that like button to support more investigations into the extreme physics that reveals the deepest truths about reality. Subscribe to our channel and hit that notification bell so you never miss our journeys into the impossible scenarios that illuminate the possible principles governing our universe. Share this video with anyone who's ever wondered about the relationship between energy and destruction, because Hawking's analysis shows that even impossible scenarios can reveal profound truths about the nature of physical law. And let me know in the comments, what other impossible physics scenarios would you like to see explored? How do you think the cosmic speed limit affects other aspects of physics and cosmology? What connections between energy and spacetime do you find most fascinating? Drop your thoughts below and join our community as we continue to explore the mathematical boundaries where impossible scenarios reveal the deepest truths about the elegant structures that govern reality itself.